All right, ladies and gentlemen, we're going to look at what's called the binomial theorem today. And what we're going to do is expand a binomial using what's called the binomial theorem. So we're going to use the binomial theorem to show you that we can actually speed up the process to expand things. So let's just review real quick on how to expand this right here. By default, what we probably did was something like this. If we didn't have the rule memorized, you would write them back to back like this, a plus b times a plus b. And then you either did FOIL or double distribution to get something a squared, then a times b is ab. Continuing on, b times a. B times a is the same as ab, but I'll write it like this for now. And then lastly, b times b is b squared. Now I combine my like terms, a squared plus 2ab. Why? Because ab plus ba, those are the same. And then lastly, plus b squared. So notice what I'm not doing. Do not say this, a squared plus b squared. This is not the distributive property of exponents. Do not send that 2 in and stop there. Notice a squared and b squared are both there, but there's another term there that shows up when you do your double distribution. So please take a moment to either jump to the shortcut if you know how, or just expand BC. Go. So we can use the quick shortcut rule to get to these ones. So this one right here, a, that one's fairly straightforward. We already know that x squared plus 2xy plus y squared. Now, on part A, it asks me to write down just the coefficients. Just the coefficients. So here's a 1, here's a 2, and here's a 1. So I'm going to write those, list the coefficients, a 1, a 2, and a 1. Now, please take a moment and take the previous, this trinomial right here, this trinomial, and multiply it by another x plus y. What do I mean by that? Well, we already know that this is going to be x squared plus 2xy plus y squared times another x plus y. What do I mean? Well, x plus y times x plus y times x plus y, because there's 3, is going to give me x plus y squared, which is that, times another x plus y. So take a moment to distribute those and see what you get. If there's not room there, you can use the very, very back of the pages to do that, or on the bottom there. Now what we can do is combine like terms. Here is an x squared y, and there's 2x squared y. So those combine to be 3x squared y. Next, I have xy squared, which coincidentally is also the same coefficient, 3xy squared. And lastly, the cubic term. So notice what started out as 6 terms here combined to be just 4 terms. So what are my leading coefficients here? I have a 1, 3, 3, 1. A 1, 3, 3, 1. So I'll put that here, 1, 3, 3, 1. All right, maybe just to save us a little bit here, this ends up getting to be something like this. We end up with x to the 4th plus 4x third y plus 6x squared y squared plus 4xy cubed, and then one more term, it's my quartic term, plus y to the 4th. And so what are my coefficients here? 1, 4, 6, 4, 1. Is instead of doing all these operations, again, this is a 4 multiplications, plus we have some combining like terms. This one is 6 multiplications plus combining like terms. This one is 9 multiplications plus combining like terms. So just to get to the answer there, I have to do 12 steps. And that's only x plus y to the 4th power. What if it were x plus y to the 10th power? That gets absurd. So of course we ask ourselves, is there a faster way? And that's what we're going to look at, what's called the binomial theorem. So here's our friend Pascal's triangle. And the background of it is simply, Pascal noticed that as you start setting up these binomials, you end up with a pattern. And the pattern is that every single row just increases by one more term. That's it. And notice that the coefficients are just a sum of the two above it. So notice here, those two add up to be 3. These two add up to be 3. Notice the ones are always ones on the inside and outside. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So Pascal noticed that there's a nice little pattern that results here. So Pascal's triangle will look something like this. So a 1, then we get a 1 and a 1. This one's a 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 5. 10 again. 5, 1, 1, 6, 15, 20, 15, 6, and 1. So all this is helpful because what this does is it helps us to generate the coefficients. This helps us to generate the coefficients of my binomial. But what other pattern do we notice here too? Look at this guy right here. Where do we start off? What's the highest exponent there? It has a 4. But then what happens to the x? What does it do? Goes down how much? 1. Go down another 1 to go to 2. Then go down another 1 to 1. And then go down another 1 to be gone. So notice the x part, or the first term starts at to the 4th, 3rd, 2, 1, 0. Gone. The second term, the y, goes from a 0 to a 1 to a 2 to a 3 to a 4. So that one's increasing while x is decreasing. So notice that this is a pattern that can easily be replicated. So let's now look at what the binomial theorem is. Here is the binomial theorem. For every positive integer n, a plus b to some power n, to the power of 1, to the power of 2, to the power of 15, it doesn't matter. All we're doing is taking a binomial and raising it to some power. What we're doing is we have some coefficients, so notice what the p's there just represent coefficients. So these are the coefficients here, here, and here, and notice what they are. They're part of the Pascal triangle. Okay, so that's the first part. The second part is, notice how a to the a decreases by 1, decreases by another, etc. And the b increases as you go. The exponent increases. All the way until the b is at its max and the a is at its lowest to the 0. So let's unpack this one here. So how do I rewrite this using the binomial theorem? Well, I do know what my coefficients are. They're the 6th row. So I know what my coefficients are. They're 1, 6. What was the 15? Oops, I'm going to need some space there. 15, 20, 15, 6, and lastly 1. Okay. Next, how do I get from my first term, which is right here, all the way to my last term? Well, all I do is take this right here. Whatever's here. Here it's just an a, but if it were 2a, I would say 2 times 2a to the power of 6 or whatever. So now I take this a and I raise that to the 6th power. So let me just follow that pattern, and that's a is going to drop. A to the 5th power, a to the 4th power, a to the 3rd power, a squared, a to the 1 power just by itself, and the 1 in the very end has no a. Poof, a to the 0. Now, I take my b here, and the b is going to be raised. I'm going to take the plus b. I pay attention to that plus, because that plus is important. So my plus b, now I'm going to start off with no b on this first one. Then this one is b to the 1 power. So this one is b to the 2 power. This one's b to the 3rd power. Keep going. B to the 4th power, b to the 5th power, and this one's b to the 6th power. Now, what is separating every term? In this case, everything that's separating is going to be the plus. Why is it all plus? Because look, a and b are both positive as they're represented. So let me go ahead and put addition in between every term. And we'll get to the dealing with some negatives in a little bit. Positive in between everything. Now, I do want to simplify anything that can be simplified here. And it turns out the very first term and the very last term can be simplified because I don't need to write the 1. So let me just go ahead and simplify. A to the 6 plus 6a 5b plus 15a 4b squared plus 20a cubed b cubed plus 15a squared b4 plus 6ab to the 5th plus b to the 6th power. Let's take a gander at this one here. Since this is to the 4th power, I need to go to the 4th row of the Pascal triangle. So the 4th row always starts with 1, and it always ends in 1. 1, 4, 6, 4, 1. Now I am going to put a plus. I'm going to go ahead and put the plus in front of everything right now. Right there. Because the negatives will show themselves in just a minute. The negatives will show themselves in just a minute. Okay, the first thing I need to do is take this x, and I'm going to distribute its pattern. So I start at the 4th power, because that's its highest, and then all I do is decrease it. 3rd squared x to the 1, and I don't even need to write it at the end, because x to the 0 drops out as a 1. Now here's a little bit more confusing. The second term is not a b, like we had earlier, it's a negative 3. So I don't write it in the very first term, but I do have to write the negative 3 here. So notice how I'm going to place it as a parenthesis with a negative 3 there. Now I have to increase its exponent. So this one's going to be a square. This one's going to be a negative 3 to the 3rd power. And this one's going to be a negative 3 to the 4th power. So this is where simplification is going to have to take place a little bit more. The first term is just x to the 4th power done. Notice this though. I have a 4 times 3 is 12. And don't forget there's a negative right there. So negative 12x to the 3rd. So notice we're already outside of Pascal's triangle. Originally, Pascal's triangle, 1, 4, 6, 4, 1, is just there to help me set it up. The final result might not resemble the triangle. All right, now let me multiply here. I have a negative squared is positive, so this is a 9 right here. Times 6 is 54. 54x squared. Next, I have negative 3 cubed, so that's negative 27. And I have to multiply that by 4, so we know I will get a negative right there. And to get 108x. And lastly, negative to the fourth power is positive. And then 3 to the fourth power is 81. Let's look at C now and show you that it does get a little bit more complicated. So, and that's where we'll end with its complexity. All right, so notice I start at the power of 5, so I'm going to go to the fifth row. 1, 5, 10, 10, 5, 1. Now I need to take a look at my very first term. Notice my first term is 3x. So it's not just the x that's get raised to the power, it's also the 3. So notice I'm going to put the 3x in parentheses, and that's a 5. So let me just clean that up. There we go. 3x to the fourth power. Next, 3x to the third power. This one is 3x quantity squared, so all of it is squared, not just the x. This one is simply 3x, and the 3x drops out by the last term. Yes. Now notice what my b term is. My second term is a negative 2. So I'm going to increase the exponent. Notice I have to place the negative in the parentheses as well. So that's negative 2 to the first power. So this one is negative 2 squared. And this one is negative 2 cubed. This one is negative 2 to the fourth power. So this one has to be negative 2 to the fifth power. Now to simplify each one of these accordingly. So how do we do that? Well, this one I have to take and say 3 to the fifth power. That's 3 times 3 times 3 times 3 times 3. 243 x to the fifth power. Now this one, notice I put a plus, but I have to double check that. I'm going to undo that. It's not actually a plus, it's a minus. Why? Because this negative 2 is a negative. So I have to do 3 to the fourth power, that's 81. I have to multiply it by 5 and by 2. So that one's 810 x to the fourth power. Next, we're back to a positive. Why? Because the negative squared is positive. So I'll put a plus here. And this one says I have 3 to the third power, that's 27, times 4 times 10. 20 x squared. Next, back to positives. Why? Because of negative to the fourth power is positive. And 3 times 16 times 5, 240x. And lastly, we're back to negatives. And 2 to the fifth power is negative, or 32 with a negative there. So notice my final answer is not a mathematical palindrome. Doesn't have to be. It might be, but it doesn't have to be. So in this case, we end up with what looks like a lot of HD televisions, 1080s, 720s, etc.